All right, welcome back to the last session of the course from my part. Let me remind you briefly what I was talking about when we stopped earlier today, which is looking at possible new physics effects involving the Higgs. And here, these are not the only possible effects involving the Higgs. Those are the ones that change the coupling of the Higgs to the standard model particles. And as I mentioned, this is parameterized by this series of constants that are called C sub W, Z, and so on. And and these are the things experiments tend to measure. And I'm going to look at these things a little bit, trying to express them in terms of the Wilson, as it's called, the coefficients of the effective theory, C sub O, and make some comments along the way that I think will be illuminating in considering which of these effects may be or may not be large. You notice that I did not include couplings to the up and down quark, to the electron and the muon. The reason for that is that these are in the standard model, they're very small. They're proportional to the corresponding masses divided by the vacuum expectation value. So very small. And since we don't see any corrections to the standard model effects at low energies and at the LHC, which involve these electrons, muons, up and down, charm and strange quarks, they are not included in here. In principle, this can be extended to everything, At the LHC, these are the things that have a chance of being measured. So I mentioned that the operators that come into play in this exercise can be classified into these three categories, and I'll go through them one by one. So let me first go to the pure Higgs operators. These are two of them. There's two of them, simply. This guy and this guy. Now, when you write down the Higgs, the scalar doublet in terms of the Higgs and the vacuum expectation value in the unitary gauge, you replace phi basically by this expression. And so when you add this object here, this first one, to the Lagrangian, what you get is a term that goes like the standard model that includes a term that goes like 1/2 dh squared. This is the standard model piece. And then when you put this thing here, it generates, among other terms, this object, epsilon c d phi squared, where epsilon hereafter will be v squared over lambda squared. When you look at this thing, this object changes, among other things, the mass of the Higgs, the VEV, and many other things. This I will not talk about, because this doesn't involve the couplings of the Higgs to the fermions. But this does, because in order to have a properly normalized kinetic piece, one needs to do a finite renormalization. That is, instead of considering the little field h here that comes up here, we should consider this field instead, that we'll call capital H, the physical field, which is related by a factor with a little h. So what one has to do to take into account the presence of these operators is replace little h by big H everywhere. Okay? So that's one effect that one must take into account. So this is it. As I mentioned here, phi to 6 changes V and can be absorbed in finite renormalizations. This can be proved only by looking at Higgs self-interactions. Higgs triple quartic, quintic, and sextic vertices of the Higgs are generated here, but those are not they're not the ones that we're talking about. So not interactions we're talking about here. And so I will not talk about this guy. I don't have to talk about this guy. What is important is that what this does is change the canonical normalization of the field. And in order to return to a properly normalized field, one has to replace little h by h everywhere. That's it. That's what the pure Higgs operators do. Any questions? Okay, second group. These are operators that modify the couplings of the Higgs to the W and to the Z directly. In fact, there's only one of them that is generated among all the PTG list, and it's only this guy. This guy indeed does modify the coupling of the Z, the coupling of the Higgs to the W and the Z, but it does something else also. It changes the vacuum polarization of the Z. And so, without affecting the vacuum polarization of the W. Therefore, that makes a change in the canonical relationship where it says that MW is the MZ times the cosine of the weak mixing angle. That relationship is modified by the presence of this operator. And the difference has a name, is the oblique T parameter. In the standard model, the oblique T parameter is 0, and at tree level. And therefore, this operator changes that. Instead of being 0, it is this thing. This is a subindex. So this is a C sub phi d, like there. C sub phi d times epsilon, which I remind you, it's v squared over lambda squared, and divided by alpha, and that alpha shows up because of the definition of what the oblique parameter is. And so in the standard model, this is 0 tree level, and it's been very precisely measured. When I last checked, it was the order of 10%. And what happens then is that because of these constraints, the effects of this operator on the Higgs couplings, now on the Higgs couplings to the Z and W, are too constrained. That means, what I mean is, they are required to be very small, too small to be distinguished from the noise given the precision of the LHC. So this operator can be ignored just because this constraint ensures that its effects are below the LHC sensitivity. And I'm going to do this several times. If a collider or low energy experiment or whatever data implies that the coefficient of an operator is sufficiently small, I just drop it. I will not talk about it anymore. Not because it's not interesting in general, but because at least currently the effects are known, because of this constraint, to be below the LHC sensitivity. The rest of the operators that connect the Higgs and the vector bosons, all these guys, are loop generated, and again, they can be neglected to a first approximation because they have this inherent suppression. Therefore, the conclusion is that the HZZ and HWW couplings will be standard model to lowest order. Any questions? Okay, we're done with group number 2. Let's go to the last one. Now there's the coupling of the W and Z to the fermions. There are many. These guys that have this derivative to the leptons, to the quarks, and then this extra guy that couples to an up and down with a charge conjugate doublet here. All these, if you expand them, this guy, they generate a term that goes like fermion Z slash, the Z field, fermion. Fermion Z slash fermion. Similar here. Here generates up W slash D. What that means is that all these guys do is modify the coupling of the fermions to the Z and the W. But those have been very well measured by LEP, and by LHC, to the point that the constraints require lambda to be greater than 1 TeV in all of them, except for the top quark, And they lead to only 1% corrections to the standard model, or smaller, and they are again below where the measuring these couplings to 1% is certainly not below the LHC sensitivity. What is below the LHC sensitivity is the effect of such 1% corrections would have in the Higgs couplings. Okay, so that is what's going on here. The effect of this on the Higgs couplings to the various particles is it's not precise enough, those measurements, to be able to detect this type of effects. So all these guys I can drop, except for the top. Again, it's noted here. And the loop-generated guys are, again, too small. They will have an inherent suppression factor, and they'll just drop. Any question? So the last set. So the H coupling to fermions, scalar coupling to fermions. These are these Yukawa-like couplings. This is the standard model Yukawa coupling multiplied by phi squared. That's what they are. In unitary gauge, this object, phi squared, and I forgot to divide by lambda squared. I apologize. So this is phi squared over lambda squared is epsilon over 2 V plus 3H plus blah, blah, blah. Okay, let me write down this. So phi squared over lambda squared is epsilon over 2 V plus 3H plus blah, 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 blah. So what does this guy do? This guy modifies the mass of the electron, or the Yukawa coupling of the electron, and of the fermions. So the whole Lagrangian contains a term that goes like this. Yukawa, and I'm going to just look at the generic fermion. You have something like L bar E phi. I'm sorry, I used the wrong phi. Okay, L E phi plus this guy plus C over lambda squared phi squared L bar E phi. So let's see what we get from this exercise. What we is the following. So we get Y plus epsilon V I think I made a mistake. I'm sorry. It goes like this. Epsilon over 2 V over root 2 times L bar, actually, sorry, that goes like E left, E right. This is what we get for one term. And, I'm sorry, it goes like here. Sorry. And then we have another term that involves the Higgs, and that is Y plus epsilon over 2 times 3 and H over root 2 E bar E. And there are other terms. So this can be absorbed in a renormalization of Y. Just shift Y. But so this disappears, and so you get the standard expression for the mass of the electron. But when you do that shift, you cannot then eliminate this guy. You can absorb, if you wish, 1 epsilon over 2, but 2 remain. And so there is a shift in the coupling of the Higgs to the fermions. In addition, I have to replace little h by big H. So, so there is some modification to the coupling of the fermions, and therefore I must include these guys. These are not necessarily as well measured as one like. because, I'm sorry, the masses are very well measured. This coupling is not very well measured. The one of the Higgs to the fermions. In fact, that's one of the goals of the LHC. Finally, let me look at some loop-generated operators. Because, as I mentioned, some of the most interesting processes involving the Higgs, well, and necessary processes like the production of the Higgs involves the HGG, gluon-gluon coupling, which is loop-generated. And because of the interesting decay of the Higgs to two photons and to Z gamma are also loop-generated, then effective operators that are loop-generated themselves that interfere with the standard model will be, in principle, will give, in principle, large enough effects that can be measured or constrained given the LHC sensitivity. Because we're comparing apples with apples, the standard model is loop, these guys are loop. And the interference term goes like 1 over lambda squared, and we're good. The terms that are loop generated and can be ignored are those that do not interfere with the standard model, because then their effects are 1 over lambda to the fourth in the cross-section, because the cross-section is square of the amplitude. There is no interference term that would give a 1 over lambda squared. And in addition, they have a 1 over 16 pi squared suppression. So these we will ignore. And in particular, those are the ones that include x tilde, where x tilde is the dual of the corresponding field strength. Okay? Questions so far? All right, so let's see what we get. So the phenomenology. So the coupling of the H to two fermions, well, it's related to by kappa or C. I changed to kappa because C became now very confusing. Kappa squared of the standard model value. And in our case, kappa squared, if you do everything carefully, is this thing. This comes from the renormalization of the Higgs, and this comes from these operators such as the ones here on the board. You can also calculate the Higgs to VV star, that is producing a physical Z or W and a virtual Z or W thing, which was one of the discovery modes of the Higgs. And you see that, in fact, this, as I argued, this vertex here has to be standard model within the precision available. This also, and this actually is very small for the same reason. And I'll come back to this in a second for the same reason. And therefore, this is affected only by the wave function renormalization of the Higgs potentially. All the other effects are there, but they're too small. Why is this guy very small? I'll tell you. The reason is that this comes from this vertex here, Z8. Because these operators, I told you, I'm going to go back to the board. I told you they generate modifications to the coupling of the Z to the fermions. But they do more. So, when you have an operator like this, D back and forth, phi dagger, fermion, gamma mu, fermion, and you expand in the unitary gauge, you get a term that goes like V squared, psi bar, Z slash psi. But that's not the only term. That term comes from replacing these guys by the VEP. You get other terms that go like V squared, H, psi bar, Z slash C, and things like that. And many other terms. Pardon me? Yeah, the H over V. Sorry, yeah. you get this term, and many others, or several others. There's like 4 of them, several others. Okay, so what I'm telling you is what LEP constrains is this guy, it's coupling. So the coefficient of that guy, of this full operator, is constrained by the LEP data and by the LHC data, the coupling of Z2. And therefore, since it's a coefficient for the whole operator, so will be the coefficient for this operator. And therefore, if this is small, this has to be small because it's the same coefficient. And therefore, I can drop this, guys. And this is the only quantity that's measured. Lastly, there is the coefficient, the modifications to the 2 photon Z gamma and GG couplings, and you get this horrible thing. Why? Because of various loop effects that you take into account. The standard model, this comes from interference between the standard model and the effective theory. The standard model is a one-loop effect. And so you have to evaluate a loop. And the loop doesn't give a number like 3/2 or a nice rational number, but just numbers that depend on the masses in the loop, the top quark, the W, the G, the gauge coupling constant, things like that. And so you get funny numbers like this from that. But that is just comes from the interference terms. It's an interference term because all these things will be proportional to epsilon. Epsilon goes 1 over lambda squared, and that has to come from the cross term between the standard model and the effective theory. And here you have these guys. Okay, let me go back. So this is the translation of things. So why is this useful? This is useful, I should say. This is useful because in the language of the kappas, you're just measuring numbers. In the language of the Wilson operators, Wilson coefficients, you can relate those to specific operators whose underlying physics you can try to unravel. The effective operators, being gauge invariant, in a sense are physical. They satisfy all the symmetries of the standard model, and so they have that going for them. This expression that I started with is very simple, much simpler than the effective theory, but it has a problem. There is no connection between between this type of coefficients, or if you call them kappa, kappa W, kappa Z, and any kind of underlying physics. They're just numbers. There is no reason to suppose that this CW will be of this precise form in the standard model effective theory. There is no reason to suppose. What this is concluding, for example, is that any reasonable kind of new physics, to a first approximation, will give the same modification to the W and Z couplings. Something that, can be tested in principle. So if someone finds a deviation from the standard model in this type of decay for the W, H2W, W star, then the same magnitude of deviation or percentual deviation should be found in the Z decay, if this is to be consistent. This is a direct prediction of this theory. The similar for these things, there is no reason to suppose that these particular expressions will hold. On the other hand, this is a result that connects, as I said, in a way, the physical underlying theory with the coefficients that you actually measure. Notice that there are more than 3 coefficients involved here. There's 1 here, 2, 3, 4, 5 coefficients involved here. And we have only 3 numbers. So that might be discouraging. You say, well, we'll never be able to separate these guys from one another. and we'll just get limited information. That is unfortunately often the case. The data that we can measure relatively easily, that we can obtain relatively easily, is not sufficient to be able to distinguish all possible combination of operators. So it's impossible to differentiate between a non-zero Z gamma gamma and a non-zero C D5, for example. But there's one exception, and that is the exception, and that corresponds to the case where all operators are loop generated. In that case, this is true. And we have certainly enough data, 1, 2, 3 data points for 1, 2 coefficients. Yeah, pretty good. And so we can put a limit on lambda based on this thing, which is 1.4 TD.
Is basically that you kill those tree generator operators by hand.
What happens is, not by hand, I choose the right model, supersymmetry. I choose the right model, not by hand, not by hand. There are models where there are no tree-level generator. And then what happens? So let me go back to this here. So see what happens here. This gamma gamma, is tilde, came from loop-generated operator coefficients. This, by the normalization that I've chosen, these guys are from loop-generated guys. This goes like 1 over 16 pi squared. But I'm explicitly multiplying by 16 pi squared. So this in general is of order 1. Okay. And that's just manipulation. There's nothing deep in this. It's just a manipulation of the expressions. There's no similarly here. So this is order 1, order 1, order 1. And that's why, and it appears here in this combination. Now, if everything is loop generated, these guys will be loop generated as well. So whereas these guys will be of order 1, now these guys will be tiny. This will be tiny, and I can just drop them. And so when you measure H to gamma gamma in that kind of new physics, you will measure C tilde gamma gamma. When you measure this, you measure this. When you measure this, you measure this. Is a one-to-one correspondence between data and unknown coefficients. You can start mapping out your effective theory. Okay. And that is the special case. And from the data at the LHC, maybe this probably has improved by now, because these measurements have become more and more precise as time goes on. So this is a lower limit. I don't know. But at least it's one case where existing data is sufficient to put an unambiguous limit on the...
So this is assuming that this C tilde GG is 1 by 16 pi.
I'm assuming, okay, these guys are always 1 over 16 pi squared. Or sorry. These guys may or may not be, depending if this is, but in the type of physics that where this is 1 over 16 pi squared, those go away. In the type of physics where they do not, then you can't tell that whether, suppose you get absolutely, measure this with incredible precision, and you find that you get exactly the standard model 1. So you get 1. That doesn't mean that this and this are 0. It just means that this linear combination is 0. So there could be some cancellation. Okay? And so the point of what I'm telling you is in the case where there are no PTG operators, not tree-generated operators at all, then that cancellation cannot occur because the leading effects on all these measurements come from only 3 coefficients that don't interfere with one another. And so there's a direct correspondence between kappa and C, kappa and C, kappa and C. There's no cancellation. All right. Any questions? This is the end of the standard model application section. Going once, going twice. Remember, this is Friday. I'm not here tomorrow. Okay. Last chance. No, actually, you can always email me, please. Okay. If not, let me go to the last application that I had in mind, and this is application to dark matter physics. Now, dark matter is characterized by 2 things. We don't know what it is. We really think that it's there, but we have no idea what its properties are. But that ignorance has never stopped a theoretical physicist from speculating using prejudice, hand-waving, and sometimes rigorous arguments to try to classify all possibilities. From what I'm going to tell you, I'm going to try to be as honest as possible. It's certainly not the only possibility. It's the possibility I like. And so you have to take that into account. I'm prejudiced for it. But and nature certainly takes no account of what I like or not like. Otherwise, I would be very rich. So then the point is that take this with a grain of salt as one possible approach to the effective theory, to the case of a large amount of stuff that's out there that's described by particle physics, okay, about whose properties we experimentally know nothing. So as Shuba mentioned earlier in the course, the latest cosmic census of matter gives about 23% of the contents to dark matter. So this is dark matter, this is dark energy. So we know this behaves like matter. We have absolutely no idea what this is, that kind of thing. And we are here. Actually, we are in a sliver of this. Most of this thing is gas. Okay, so we are just about inside the 1% of the energy matter content of the universe. Whatever information we have about this guy, which is the one, I'm not going to talk about dark energy, about this guy, is obtained using gravitational effects, and therefore we have no knowledge about what the microphysics of this dark matter is. Could be, in fact. So there are many, many models. And when I say it's the simplest, again, it's the simplest for me. It might be very complicated for others, but it's for me. And I'm not going to write for me because it looks awful on the slide, but yes, keep it into account, okay? So many models, the simplest that I thought of is the following. There are two sectors, us and them. And we have mediators between the standard model and the dark sector. Yeah. Okay. If the mediators are heavy compared to the scales, they can be integrated out, and you get an effective theory that generates operators like this. You get the standard model coupling, the thing mediator couples to in the standard model, and the thing the mediator couples in the dark sector, and I've integrated out, which in this simple vision, and I'm trying to consider a simple scenario, it's just kind of a propagator between this and this. So you get 1 over p squared minus m squared. I'm telling you, the momentum p squared is much smaller than m squared. And so you just get m to some power. And I'm putting m to the k because what happens if it's a fermion? Then you get 1 over m instead of 1 over m squared. So that looks familiar. I mean, it's just another effective operator. So I will assume the following things. All dark matter couplings to the standard model are, all dark matter particles coupling to the standard model are non-singlet under some group GDM. That is, they couple via the mediator. So any part of the dark sector, could be all the dark sector, but could any part of the dark sector that actually participates in this interaction transforms non-trivially under some group GDM. There are many choices for GDM. Doesn't matter. Many choices. You can choose Z2, it's very common. You can choose a gauge group, that's also common. It doesn't matter, just a gauge. I will not need to specify. The dark sector has particles of spin less than 1, but I will not. I will assume that an antisymmetric tensor field, which also describes spin 1 particles, is not there. A prejudice. The reason is I don't know how to write Lagrangians with this guy, so I ignore it. And I also assume that the mediators have spin less than 1. But again, no antisymmetric tensor field exchange. So the strategy I will follow is To construct the leading, that is, as low-dimensional and tree-generated standard model dark matter interactions, infer the types of mediators that can be involved, find all the standard model interactions generated by each mediator, and construct then a UV complete theory. I will not get to this part. I will just sketch it at the end. So the first thing to do is construct the leading tree-level generated lower dimensional SMTM interactions. And for that, I need to list these guys, this and this guy, in increasing order of dimension. Notice that even though I'm assuming that these guys are, I didn't write, I will assume also that the dark matter particles are singlets under the standard model gauge group. So that's a fourth assumption that I did not list. So these guys, I just need all gauge invariant standard model operators, but I don't have to assume that they're Lorentz scalars. That's not necessarily true, because the mediator might not be a Lorentz scalar, might be a vector, might be a fermion, but they also may be a scalar. So I need all these guys without the assumption that they're scalars, and similarly for the dark matter guys. Okay. Symbolically, the Lagrangian looks like this. You have P, which is the mediator, SM, P, dm, plus LP, the mediator. Fields are assumed to be singlets under both the standard model symmetries and under this guy, GDM. And they have some Lagrangian between them. And so you have this kind of thing. This would be OSM, this ODM, and you get OSM, ODM divided by some mass here. So when you square this, when you consider this, because the mediator couples to SM and DM, you must get SM, SMDM terms, but also pure standard model and also pure dark. This is inescapable. These guys can be tested at the standard model, at the LHC directly. It modifies the standard model couplings. This generates dark matter self-interactions that may be large or small, depending on the details of the theory. And this represents what's called portal couplings. That is the portal through which the standard model can look out into the dark world. I am then now going to list the operators that are of relevance. The standard model operators of dimension 1, which are gauge invariants, are just none. 3/2, none. Dimension 2, there are 2. Phi squared, the doublet squared, and B mu nu. B mu nu, B is the gauge field, I remind you, of the U1 hypercharge in the standard model. It carries no quantum numbers, gauge quantum numbers. It's a gauge singlet. It's invariant on the gauge transformations. And so it belongs in this line. Dimension 5/2, you have only one. L bar, phi tilde. Dimension 3 are these, dimension 7, 2 are these, and you can amuse yourselves going back. Okay. Now, in constructing the dark matter operators, I'm going to assume that I have a generic theory involving fermions and scalars and vectors. And I'm going to go through all possibilities. Now, dimension 1, I have no operators, not because I don't have scalars, but because of the assumption. I have the dimension 1 operator is one scalar. But that scalar, because of this assumption, transforms non-trivially under this GDM. And I've required that the operators ODM, as you can see here, I have yet another typo, ODM, this would be ODM. The ODMs are required to be singlets under this symmetry of the dark sector, whatever it is. A single field isn't. And so dimension 1 operators would be one scalar field, one vector field. They're not. If you have dimension 3/2, that's one fermion field, and then it doesn't appear because they're necessarily, because of my assumption, non-singlets on the dark symmetry. Dimension 2 are these, dimension 5 halves are these, possible dimension 3 are this mass, dimension 7 halves are these, and so you can go on listing these guys. I will stop with this. And now what I'm going to do is match them and see, well, what is the lowest dimension composite product of this times this that I can get? And again, I'm sorry, this is the that I can get, which satisfies all the symmetries, including now, because this will be a member of the Lagrangian, including Lorentz invariants. So the lowest dimension you can get is 2 times flu, is a 4-dimensional operator. I can multiply this by this by this, and I get a singlet. That's good. I can multiply this by this, and it's not good because I get a Lorentz tensor whose indices are not canceled by anything, not contracted with anything. So this times this doesn't work. The earliest I can contract this with anything is with this guy over here. Which brings me to one question. How is this a singlet? Okay. This is the field strength of some dark vector, and phi is a scalar. This is not a singlet. And this, if it's just a U1, like here, would be a singlet. So that would seem to disallow this thing in all cases. But it's not. There is one, if X is a singlet, is a U1, corresponds to a U1, then X mu nu is a singlet. But it still can have other symmetries. It can still have other symmetries. So under those symmetries, then X mu might transform into, I don't know, minus X mu, like a parity. And phi might transform into minus phi, the parity. So it is a lot. But there's another possibility which is also worth keeping in mind. If X is in a non-abelian, gauge field, X mu nu transforms like the adjoint. Has a little index here, the adjoint. If phi A is also transforms non-trivially onto the gauge group, on this gauge group, whatever it is, and in the adjoint, this object will be a singlet under the non-abelian gauge symmetry, be a singlet on the non-abelian gauge symmetry, and that would be the, and therefore it is acceptable. I bring this up because just to illustrate the fact that the symmetry in the dark sector doesn't have to be a global symmetry. It can even be a local symmetry, provided none of the particles are singlets under it. So, and what I'm going to do is list the very few lowest dimensional combinations that I have. Again, with the same spirit, lower dimension combinations will lead to lower dimensional terms in the Lagrangian and to fewer suppressions of 1 over mediator mass as in their coefficients.
Will this be Lorentz invariant?
Pardon me?
The X mu?
No, this is not Lorentz invariant. This is not Lorentz. It is invariant under the gauge symmetry. But what I can do now is, if I'm looking at this interaction with the dark sector, I can contract it with the B mu nu in the standard model. I get a Lorentz singlet, and it's mediated by something. Okay?
Independently of the dark sector term, will it exist?
The what?
In a completely dark sector term, it will contract with its own.
Yeah, in the complete dark sector, you can have that quantity squared, also mediated by whatever thing mediates this. Okay? In this fashion. So let's look at what we get. The lowest dimensional term is two scalar doublets in the standard model, two in the dark sector. The next orders have dimension 5 operators like this, 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 and this. And the thing that goes between them, and this is the picture I have in mind, that it talks on one side to the standard model, is a scalar that couples to phi squared and a scalar to psi bar psi, a scalar that couples to phi squared and to phi cubed. You might ask, well, what is it? And the answer is, I don't know. I don't know whether they're fermions or scalars. In some dark matter models, they're only scalars. In others, they're just fermions. In others, there's both of them. So this just describes generically, for any possibility, what kind of couplings can you have. If the mediator is a fermion, you get this type of thing, which will be something I will talk about extensively. If the mediator is a vector, you get a product of two currents. For consistency, the currents have to be conserved. I'm assuming that can be arranged in the standard model, in the dark sector. In the standard model, that's much, well, I cannot just assume it is conserved because I know all possible currents. One of them that is very useful is the current associated with V minus L. It's automatically conserved. And that's for consistency of having a vector field. Vector couples to conserved currents. And in this case, the vector I'm assuming is an abelian, corresponds to some abelian gauge group. There are other dimension 6 operators, and these are subleading in the sense that they're generated by the same guy coupling to the same type of field, and so they will have higher dimension produced by the same type of effect, and so that's why I call them subleading. In the same way, here it is coupling the same fields, but one with the derivative, and so I call it subleading. Operators like this are loop generated because I've assumed there are no mediators that behave like an antisymmetric tensor field. So these have names by now. This coupling of dark to standard model is called the Higgs coupling because cleverly it involves the Higgs. This is called the neutrino portal because, as you might guess, perhaps unsurprisingly, it involves a neutrino. This is called the vector coupling because it's a vector-mediated interaction. All of them have been studied extensively, some of them to death almost, like the first one. And in fact, right, but I will talk about this guy very briefly, once, from the point of view of effective field theory, I'm done. I exhibit for you the Lagrangian. The rest of the thing one can do is just apply it. It's another Lagrangian. I just do calculations. Okay, so I'm going to assume that the mediator is a fermion. I'm going to assume that there are two components in this, at least in the dark sector, one fermion and one scalar. So I can construct this, and therefore you have a tree-level a coupling generated by this guy between the standard model neutrinos and the dark sector. This coupling will determine the relic abundance. Now, within this scenario, there is no direct coupling of the psi, the fermions in the dark sector, or the phi, the scalars in the dark sector, to the Z and to the Higgs. But these are generated at one loop. I'm briefly going to show that in a minute because I'm running out of time. The point of this is that the interaction that determines the direct detection of dark matter involves dark matter scattering off a nucleus. And this is achieved in this model only through the interaction of a mediation of a Z or a Higgs in the T channel. These interactions are automatically suppressed, which means that the direct detection cross-section is automatically small compared to the relic abundance, the cross-section. And this is what I liked about this model. We know there's a relic abundance of dark matter. We know it, but we haven't been able to see it. So this model automatically tells you that it's relatively easy to generate dark matter in the cosmos because it couples to neutrinos, but it's very hard to detect because its couplings to baryons are strongly suppressed. So the leading interactions are these: neutrino, phi dagger, psi, like this. The subleading interactions are these. They're suppressed by loops. These are not, they are not necessarily loop-generated operators. If you had a scalar mediator, it could mediate between two Higgses, a scalar, and two fermions. I mean, there's no problem with that. I am assuming that such a scalar does not exist. Okay, so I'm restricting further things. I can make a consistent model of it, so in that sense it's justified, but it's not the most general situation. I'm mixing a prejudice of what kind of mediators are there, what kind of new physics is there underlying, with the effective field theory approach. From this, I can do everything. I can calculate the relevant cross-section that determines the abundance of the dark matter in the current universe, and use the data from the Planck experiment to constrain the thing. And in this calculation, I'm going to assume that the fermions, the dark fermions, are lighter than the heavy fermions, than the dark scalars. If the guys are lighter than these guys, then along the way, these guys all decayed into fermions and neutrinos. So in this scenario, it is here. In this scenario, the dark matter is fermionic. You can assume the other way, but that goes back really to a Higgs portal dominated scenario that's been studied. So this is just an attempt to study an alternate scenario. That assumption. And so you get this type of constraint on the theory. This is the allowed value of this lambda f. Lambda f is related to lambda, which is the mediator mass. F is a coupling, and you have the masses of the two dark particles. You can do a more refined calculation involving the Z and the Higgs that are usually irrelevant because this coupling is very small, except when it hits the resonance, that is the mass of the Z and the mass of the Higgs. Here's the mass of the Z, here is the mass of the Higgs. It's much narrower, so the effect is much more dramatic. And this is what you get for the limits allowed on this quantity lambda effective by this, in this model. I'm going really fast because this is just applying something. The heavy lifting was done in selecting the operators. The rest is doing the plug and chug almost calculation in dark matter papers. Direct detection goes through these loop-generated operators that couple to the nucleons via the exchange of the Z or a Higgs. The relevant interactions are of this form. This corresponds to the Higgs coupling. This corresponds to the Z coupling. And from it, you can extract with significant amount of difficulty because you're dealing with nuclei, not with protons, not with quarks, with nuclei, an expression for the direct detection cross-section. And the results are very simple. This is these are the limits. It's a little bit old, as you see, 10 years old. So this thing has come down to around here, kind of thing. But these are the various, for these various predictions, this is the cross-section. You can't read this. This is the direct detection cross-section predicted by the model. These are the limits on that cross-section from the experiments 10 years ago. The limits currently are around here, Getting close, getting close. And these are the predictions of the model for it looks so jagged because of the difficulties in the complications associated with calculating nuclear cross sections. There is also the possibility of indirect detection. That is, if these psis accumulate in the universe a lot, then and they coalesce in one place, like the center of the sun, they may, through an exchange of phi, annihilate into neutrinos. This is a relatively large coupling, and what the signature is, since these guys would be sitting in the sun, they would come together, annihilate, would be two back-to-back neutrinos with energy half the mass of the psi. Again, 10 years ago, the data was very sparse. Now it's a little bit less sparse, but the predictions and the data are still far away from one another. This is the end of my presentation. I'm sorry I rushed because I just have 4 minutes to conclude. So if you don't mind, let me conclude. And if you have questions about the dark matter model, we can ask later. Is that okay after the conclusion? So I can feel good about finishing on time, and I can blame taking longer on you. Okay, that's the plan. So let me conclude. So the EFT, I think, provides a very useful guide for studying new physics effect. It's very good. It doesn't have absolute precision of the model. It has many couplings that can be estimated or bounded, has one scale, and so on. You can extract very useful information, like the magnitude of this scale, or if you make a measurement and find a deviation from the standard model, or you put limits on the scale. And that tells you something physical about the new physics. But that estimate is not precise. If I say lambda is greater than 2 TeV, it doesn't mean exactly 2 TeV. There's a margin of error because I don't know the coefficients with precision. I can just put a consistency limit on their value. Okay, so the coefficients can be estimated, but they cannot be interrelated as they would in a model without making further assumptions. If you have a model, then everything is, some of the coefficients that you get would be interrelated. That's great. But if you have a model, why worry about the effective theory? Radiative corrections can be obtained. The effects of the renormalization group are limited unless lambda is much larger than v. That is, unless you run from a very large scale to the electroweak scale. Okay, they can be, but in this case, the 1 over lambda n per factor can suppress the overall effect. So the overall effect of the renormalization group running of coefficients are minor unless there is a huge mass gap. It has been extensively studied, this approach. There is even a working group, a standing working group in the community doing this. This is, so there's a renewed interest in it, precisely because of the possibility of probing democratically all types of new physics using it. However, some studies are misleading or incomplete. That's decreasingly so, fortunately. Many experimental papers include only loop-generated operators. All the experimental papers, they put coefficients of order 1, and then they obtain very strong constraints on the scale of new physics. Those are misleading. Or sometimes the calculations don't include all relevant operators, which an exercise can be really scary because there could be very many included. But then the possibility of cancellations is disregarded. Cancellations are not a contrivance. Cancellations occur all the time in models, all the time in models. We had one expression, one of the exercises given to you in the tutorial about the strong interactions, ask you to calculate the scattering of pions. You would have found that the cross-section increases with the center of mass energy. And it does so precisely because there's a cancellation. It's not an unnatural fine-tuning. It's inherent to the structure of the theory. So cancellations can occur. Okay, they oftentimes are evidence or signals of something rather interesting or profound happening, but at the level of the effective theory, we might not be able to see this. On the other hand, ignoring the possibility might lead us into missing something. So if you don't include all the relevant operators, you can't see what possible cancellations could occur, and you might miss something. And there are things that have not been studied thoroughly. So finite temperature EFT is not very well studied. Effects of EFT on CP asymmetry in the early universe also have not been studied. And so there are also theoretical questions that people in the Institute can readily answer. Like, for example, why all dimension 7 operators violate B minus L, I should say B minus L. So this is one of many things. So I hope I've given you an overview over which I've rushed, and now I've overstepped 1 minute, which I apologize, of the field. The review by its own nature is incomplete and prejudiced, and so nonetheless, I hope it has given you a flavor of the many exciting projects, the many interesting and challenging calculations and ideas that are involved in looking at this type of approach to quantum field theory. Thank you. Okay. Now, questions? Yes? Yeah?
No, not this one. Yeah, this one. So there is a dip around 60 GeV, right?
Is it what?
There is a dip around 60 GeV because of threshold.
This is the Higgs. This is, I think, the Higgs. It happens at the mass when the mass of this guy is half the mass of the Higgs.
Yeah.
It's an interference effect that kills it. Yeah. Sorry. Okay. Extracting an indirect detection signal for dark matter is very challenging because it's contaminated by astrophysical sources which we just don't know enough of. And so even the case, I'm telling you that there's a very smoking gun signal that is a monochromatic neutrino beam coming. There's more. It has to come out 2 neutrino beams coming back to back. That's what you're supposed to see, right? That is, detecting one beam is very challenging. Detecting one beam on the other side of the sun when you're here is very challenging, okay? Other questions? Yes?
So, yeah, I have a naive question, the 2-part question actually. The first part is that you have calculated, you have shown that any discrepancy between the measured and calculated cross-section from LHC or any collider searches, that depends on how many effective operators we can write involving those processes. For a particular process, for a particular interaction, that interaction depends on all the effective operators involving the standard model particles. But the thing is that suppose we can attack that discrepancy, we can justify that discrepancy also by introducing any BSM particle.
Okay, that is precisely what this doesn't do.
Sorry?
Sorry, finish your question. Finish your question.
So first part is that how do we I mean what is the more precise justification introducing any BSM particle to justify that discrepancy between the experiment and the theory, or the actual reason behind that mismatch between the cross section could be an introduction or including all the effective operators.
Okay. So it's the same thing from 2 points of view. If when you say you include BSM particles, you mean, I think, I have a model and I
Right.
put in this model, and I calculate deviations from the standard model in that model. Okay. Okay. That is perfectly okay. That is perfectly okay. There's nothing wrong with it. The approach presented here is, what if you don't know what is the right model? If you don't know what is the right model, you can't write a BSM particles because you don't know what they are.
Right.
And so, in that case, when you don't know, or you accept you don't know, or you decide you don't know, right? Then you do the effective theory because you don't know. If you include BSM in a specific model and you say, this is it, this is the extension of the standard model, we're done, the effective theory plays no role because there is no longer any BSM to produce any effective operators. Now, if you would like to see how your particular model looks like at low energies where we're probing, you can do that. You can derive from your model a set of operators that involve only standard model particles and have some coefficients. The difference between what I've been presenting here is that in your case, the coefficients are known functions of the model parameters.
Right.
Okay? In my case, they're completely unknown. But the calculation then would be the same. The only difference is your coefficients depend on, presumably, a small number of unknown parameters. In my case, all coefficients are arbitrary because I don't know what the BSM could be.
Okay.
Okay?
Okay. Yeah. The second part of the question is, could an approach be to determine the energy behavior of the coefficients, the behavior of these coefficients or the cross section, how it depends on the energy, could be different for an effective operator approach or an BSM approach? Could this be?
So you mean the running of the couplings?
Yes.
So the running of the couplings can be obtained in two ways. Again, if you have a model, you just calculate. If you have these guys, you also just calculate. If they are represented, if they are representations of the same theory, yours is valid at all energies, the effective theory you derive from it is valid only at low energies, then the running you get at low energies would be for that scenario, would be the same as the one you get from the top-down approach. It might look very complicated, but it will be the same, provided all the calculations are done carefully. Okay.
Thanks.
Thank you. Other questions? No? All right. So thank you very much. It's been a pleasure talking to you.